Have you ever wondered why not all energy can be fully converted into useful work? In Module 7, we will explore the topic of exergy and availability in thermodynamics. This topic helps us to understand the quality of energy, where energy losses occur, and why some processes are more efficient than others. We will first discuss the concept of exergy, then examine the irreversible process of energy losses that reduce system performance, and finally, learn how efficiency can be improved in engineering and real-life application. Through this discussion, we can better appreciate how thermodynamics help industries save energy, reduce waste, and improve overall system performance. Today, I will be discussing the definition, importance, functions, and application of exergy in thermodynamics. To start, exergy is defined as the maximum useful work that can be obtained from the system when it reaches equilibrium with the surroundings. In simpler terms, exergy is useful part of energy. While the energy is always conserved according to the first law of thermodynamics, not all energy can be converted into useful work. Because of this, exergy used to measure the quality of usefulness of energy. One simple way to understand it is the exergy tells us how valuable energy is in terms of doing work, or how much of it can still be converted into useful output. Now, the general formula for exergy for a system is exergy equal to energy minus energy unavailable for work. This shows that exergy is the portion of total energy that can still be converted into useful work before the system reaches equilibrium with the surroundings. To make it clearer, let us look at a simple example problem. Suppose a system has a total energy of 500 kilojoules and 200 kilojoules of energy is unavailable for doing work due to losses and irreversibilities. Using this formula, exergy is equal to total energy minus unavailable energy. So, exergy is equal to 500 kilojoules minus the 200 kilojoules. So, the exergy is 300 kilojoules. This means only 300 kilojoules of the system's energy can actually be converted into the useful work. Now, there are a few important ideas to remember. Systems with high temperature or high pressure have high exergy because they can produce more useful work. On the other hand, energy at room condition has low exergy since it is already close to the environment and less ability to do work. Exergy also depends on the difference between the system and its surroundings. The greater the difference, the higher the exergy. This concept is also related to the second law of thermodynamics, which explains why some energy becomes unavailable due to inefficiencies and irreversibilities, such as friction, heat loss, and entropy generation. For example, steam in turbine has high exergy because it can rotate the turbine and generate electricity. Meanwhile, warm water at room temperature has low exergy because it can produce significant useful work anymore. Now, moving on to its importance. Exergy is important because it helps to us determine how much energy is actually useful, where energy losses occur, and how we can improve system efficiency. Its functions include measuring energy quality, identifying efficiencies in a systems, helping reduce wasted energy, and improving overall engineering performance. Lastly, exergy has many real-life applications. In power plants, it is used to analyze the efficiency of turbines and boilers. In car engines, it measures how fuel energy is converted into mechanical work. In refrigerators and air conditioners, it evaluates cooling system performance. It is also used in renewable energy systems like solar, wind, and geothermal to maximize energy output. In industries, exergy helps improve fuel usage. In industries, exergy helps improve fuel usage and energy management. In summary, exergy helps us understand not just how much energy we have, but how useful the energy really is.
Today, I will discuss the concept of exergy. Exergy is the maximum useful of work obtainable for a system as it reaches the equilibrium with the surroundings. In simple terms, Exergy is the useful or available part of energy that can be converted into work. The main concept of exergy is that not all energy is useful. Even though energy is conserved, only a portion of it can actually perform useful work. Exergy measures that useful portion of energy. Exergy also represents the quality of energy. High quality energy has high exergy, while low quality energy has low exergy. For example, electricity has very high exergy because it can easily be converted into work. On the other hand, warm water has low exergy because it cannot produce much useful work even though it still contains energy. Another important idea is that exergy depends on the surroundings. A system only has exergy if it is different from the environment in terms of temperature, pressure, motion, or chemical composition. For example, hot steam in cool surroundings has high exergy because it can still produce work. However, if the steam reaches the same temperature as the surroundings, its exergy becomes zero because no more useful work can be obtained. Exergy is also closely related to the second law of thermodynamics. While energy cannot be destroyed, exergy can decrease due to irreversibilities such as friction, heat loss, and entropy generation. This decrease is called exergy destruction. This means that during real processes, some useful energy becomes unavailable. Unavailable for work because it is inefficiencies in the system. In summary, exergy measures the usefulness and quality of energy. It tells us how much work can be obtained from a system before it reaches equilibrium with the surroundings.
Now let's discuss another concept in thermodynamics. Imagine driving a car. If you spend 10 liters of fuel to get to a destination, you might notice that only 4 liters actually went into moving the car forward. Where did the 6 liters go? Of course, there were loss as heat escaped from engine, noise, and friction from those tight brakes. Furthermore, you cannot collect that scattered heat and noise to magically turn them back into gasoline. That is the essence of thermodynamics irreversibility and losses, which we will tackle today. Now let's break down exactly how this works scientifically. In a perfect imaginary world, thermodynamic system would be completely reversible. When we say reversible, it is a perfect process that can run forward and backward along the exact same path without leaving any trace on the universe. Like if you compress a gas perfectly, it takes a certain amount of work, and if you let it expand back, it gives you that exact same amount of work right back. But when we say a reversible process, in real life, once the process happens, you can never spontaneously undo it and return both the system and its surrounding to their original state. Times move in one direction and so do real physical processes. The last is the losses. When we say losses, this is the penalty we pay for irreversibility. This is the portion of useful energy which is called exergy or the available energy that gets permanently degraded into useless, chaotic molecular motion because the process wasn't perfect. Irreversibility is divided into two categories. The first is the internal irreversibility. This happens inside the boundaries of the system itself, and its primary cause is friction, turbulence, and fast expansion. The second one is the external irreversibility. This happens outside the system boundaries, in the surrounding environment, and its primary cause is heat transfer across temperature gap. So where do these losses actually happen? They stem from the three main culprits that disrupt our perfect system. They convert structured organized energy into disorganized chaotic energy. The first culprit is the friction or the mechanical irreversibility. When two surfaces side past each other like a piston moving inside the cylinder, their microscopic rough edges collide. This forces the atom to vibrate widely, transforming kinetic energy into thermal energy. You can feel this yourself by simply rubbing your hand vigorously. The second culprit is the unrestrained expansion, or the other name is the fluid irreversibility. Imagine a high-pressure gas trapped in a one-half of a tank. If you open a valve and let it rush violently in an empty vacuum chamber, it expands instantly. No usual work was gathered during that chaotic rush. To pack that gas back into the first chamber, you have to actively use a compressor and expand outside electrical work. The last culprit is the heat transfer across a finite temperature difference, or the thermal irreversibility. Heat naturally flows from hot object to the cold object. The larger the temperature gap, the more violently and destructively the energy flows at a microscopic level. As the diagram illustrates, when heat flows into an engine from a high temperature, we can extract some useful work. However, due to the natural temperature drop and inefficiencies, a significant portion is discarded or discarded into the cold sink. We can never convert 100% of that incoming heat into pure work. Every single time a loss occurs via friction, expansion, or heat transfer, the universe becomes slightly more disordered. In thermodynamics, we measure this disorder using a property called entropy. Think of entropy like a spilled coffee. It is incredibly easy to knock a mug over and scatter the liquid, but naturally gathering every single molecule back into the mug perfectly is impossible. The ultimate rule governing or driving irreversibility is the second law of thermodynamics, which states that for any real irreversible process, the total entropy of the system in its surrounding must increase. While the change in entropy between two fixed points remain identical regardless the path taken, an irreversible path generates extra unnecessary entropy along the way due to internal chaos. That generated entropy is the digital footprint of your energy losses. Now let's have a scenario and apply the concept of irreversibility and losses. Imagine a high-pressure gas expands inside a cylinder to turn a wheel. Our ideal goal is that it extracts 100 joules of work. But what actually happens? Due to the real-world physics, we hit three major irreversibility. The first is the friction. The piston rubs against the wall and 10 joule loss as friction heat. The second one is the turbulence. The gas expands too fast and swirls chaotically, and 5 joules loss to internal fluid friction. The last is the heat leak. Heat escapes through the metal cylinder into the room, and 15 joule loss across the temperature gap. Now to determine the actual work happened in this scenario, we just have to subtract our ideal goal to the total loss in this scenario, which is 100 joules minus 30 joules is equal to 70 joules. It means that instead of our goal that 100 joules of work is extracted, only 70 joules of work is actually extracted in actual scenario. Where do the 30 joules goes? The missing 30 joules wasn't destroyed. It was degraded by the mechanism into the chaotic, low-quality heat. To reverse the process and push the piston back up, you must pay back the 30 joule tax plus the extra to fight friction again, proving that the process is strictly one way. In short, irreversibility is a one-way nature of your processes that permanently generate molecular disorder or entropy and prevent a system from returning to its original state without external energy, while losses represent the specific portion of a high-quality, useful energy that gets permanently degraded into chaotic and low-quality heat due to those irreversible mechanisms like friction, turbulence, and rapid temperature drops. Remember, you cannot destroy energy, but you can destroy its usefulness. Wherever a process is irreversible, a portion of your high-quality energy degrades into a low-quality environmental heat, leaving you with a permanent thermodynamics losses.
Good day everyone! I am Algian Digopong, and today I'll be discussing our topic about irreversibility and losses in engineering systems, including how engineers measure these losses. The goal Gauss-Sedela theorem in the real-world application of irreversibility and losses. First, let us understand what is irreversibility means. So in thermodynamics, an irreversible process is a real process where the part of the energy becomes available for useful work. In actual engineering system, no process is perfectly reversible because there are always factors such as the frictions, heat transfer, turbulence, pressure drops, electrical resistance, and mixing fluids. Because of these irreversibilities, energy is degraded and converted into a less useful form, usually the heat. So this results in the what engineers call losses. So there are different types of losses encountered in engineering systems. First is a mechanical losses. These are caused by friction between moving parts such as gears, bearings, and shaft. So for example, in rotating machines, some energy is lost as heat because of frictions. Second is thermal losses. This occurs when heat escapes from the system into the surroundings. Boilers, engines, and steam pipes commonly experience thermal losses. Another type is a fluid friction losses. In pipelines and pumps, fluid experience resistance while flowing, which creates the pressure drops and requires more energy and maintained flow. So there are also electrical losses caused by electrical resistance in wires, motors, and transformers. These losses usually appears as the heat generated and electrical component. Now, how do engineers measure and calculate the magnitude of these losses? One common method is by comparing the energy input and the useful energy output of the system. The difference between the two represents the energy losses. Engineers also uses efficiency to evaluate system performance. Efficiency is the ratio of the useful output to total output. A lower efficiency means higher losses within the system. So another important concept is the entropy generations. Entropy generations measure the degree of irreversibility in a process. If entropy generations is high, it means the process has greater irreversibility and larger losses. Engineers also use exergy analysis. Exergy refers to the maximum useful work sustainable from a system. When irreversibility occurs, some exergy is destroyed, meaning some useful work potential is lost. Next, let us discuss the Gauss-Sedela theorem. The Gauss-Sedela theorem explains the direct relationship between the irreversibility and work losses in thermodynamic systems. The theorem states that the lost work in a process is proportional to the entropy generated during that process. So this means that whenever entropy generation increases, the amount of useful work lost also increases. The theorem is represented by the equations W loss is equal to T OS G, where W loss is the lost work, TO is the surrounding temperature, and SG is the entropy generated. This theorem is important because it connects the second law of thermodynamics with engineers' losses. It shows that irreversibility directly causes destructions of useful energy. Sources of irreversibility related to Gauss-Sedela theorem include frictions, turbulence, heat transfer across the temperature differences, convulsions, mixings, and electrical resistance. Now, let us move to the real-world engineering application of irreversibility and losses. In the power plant, irreversibility is occurs in boilers, turbines, condenser, and pumps. Heat losses, frictions, and pressure drops reduce the overall efficiencies of the plants and increase fuel consumptions. Internal combustion engines, such as the car engines, losses occur because of the combustion efficiencies, frictions between engine parts, and heat carried away by the exhaust gases. Engineers improve engines' performance by using turbochargers between the cooling system and improve combustion control. And refrigerations, air conditioning system, compressors, and expansion valve experience water pipelines and oil pipelines, fluid friction causes pressure losses. Pump must work harder to overcome these losses. Engineers reduce them by neglecting process pipe size and smaller pipe materials. Electrical power system also experience losses due to the resistance in transmission lines and transformers. To reduce these losses, engineers use high voltage transformation system and efficient conductors. In aerospace engineering, aircrafts and jet engines experience the aerodynamic drag, combustion losses, and frictions. Reducing these irreversibilities improves fuel efficiencies and engine performance. In chemical plants and industrial processes, irreversibility occurs during chemical reactions, mixing and heat transfer. Engineers perform exergy analysis to identify the areas where energy is wasted and improve system efficiency.
Today, I will discuss efficiency improvement in energy and availability. In thermodynamics, energy is very important because it allows machines, engines, and systems to perform work. However, not all energy can be fully converted into useful work. Some of it is always wasted, usually in the form of heat. This is why improving efficiency is important. Efficiency improvement means finding ways to reduce waste energy, maximize useful work output, and use available energy more effectively. This concept is connected to availability, that also called exergy. So what is availability or exergy? Availability or exergy refers to the maximum useful work that can be obtained from a system before it reaches equilibrium when its surroundings. In simple terms, energy tells us how much energy exists. Availability tells us how much of energy can still be useful. For example, a cup of hot coffee contains thermal energy because it is hotter than the surroundings. Some of that energy can still do useful work, but once the coffee cools to room temperature, its availability decreases because no useful work can be obtained anymore. This means that energy is conserved, but availability can be destroyed due to inefficiencies. So why efficiency improvement is important? Efficiency improvement is important because many systems waste large amounts of energy. Examples of systems where efficiency is important includes the car engines, power plants, refrigerators, factories, and air conditioning system. And when efficiency is low, more fuel is consumed. Operating costs become higher and more pollution is produced. While improving efficiency helps saves energy, reduce environmental damage, lower expenses, and improve machine performance. Energy losses commonly occur due to friction, where moving parts or rub against each other and produce unwanted heat, such as in engines, where metal parts waste energy, like heat transfer to the surroundings, where some heat escapes into the environment instead of being used, like a hot pipe losing heat to air when it is not insulated, and reversibility, where real processes are not perfectly reversible, including turbulence, mixing of fluids, rapid expansion, combustion, and electrical resistance, all of which destroy availability. The general efficiency formula is N equals to useful output energy over input energy times 100%, wherein N or eta represent efficiency. Next is the useful output energy is the energy converted into desired work or the useful energy obtained from the system. Input energy is the total supplied energy or the total energy supplied to the system times 100% and converts the value to a percentage. One of the example of this is if a machine receives a 100 joule of energy and produces 70 joules of useful work. In equation, it is N equals 70 over 100 times 100% equals 70%. This means that 30% of the energy was wasted. Important concept in thermodynamics is no real machine that is 100% efficient. This limitation is explained by second law of thermodynamics, which states that some energy always become unavailable for useful work.
Now, let's discuss the methods of efficiency improvement and real-life application. First method is reducing friction. Since friction converts useful energy into heat, engineers use it as lubricants, smoother surfaces, and better machine designs. For example, oil in a car engine reduces metal-to-metal contact, improving efficiency. The second method is thermal insulation. Insulation prevents heat loss to the surroundings. For example, insulated pipes, thermos bottles, refrigerators, and building walls. By reducing heat loss, less energy is wasted, and systems require less fuel or electricity. The third method is waste heat recovery. Many industries recover waste heat and reuse it. Instead of releasing hot exhaust gases directly into the environment, the heat can preheat water, generate steam, or produces electricity. For example, in power plants, exhaust heat from turbines may still be used to boil water for another cycle. This improves overall efficiency. The fourth method is combined cycle power plants. Modern power plants use combined cycles to improve efficiency. In a simple power plant, fuel burns, steam is produced, and turbines generate electricity. But combined cycle plants use gas turbines. They reuse the hot exhaust gases to operate a steam turbine. Because energy is reused, efficiency becomes much higher. Some combined cycle plants can achieve efficiencies about 60%, which is much better than traditional plants. Next is improving engine performance. Efficiency can also improve through better combustion, proper fuel-air mixtures, advanced materials, and improved cooling systems. Modern engines are designed to produce more work while consuming less fuel. Hybrid and electric vehicles are also examples of efficiency improvement because they reduce waste energy. Now let's proceed to the real-life importance of efficiency improvement. Efficiency improvement benefits society in many ways. First, in economic benefits. Lower electricity bills, reduced fuel cost, and lower operating expenses. Second, environmental benefits. Less fuel burning, reduce greenhouse gas emission, and decrease pollution. And the third one is better resource conservation. Natural resources like coal, oil, and gas are limited. Efficient systems help conserve these resources. Energy efficiency improvement focuses on maximizing useful work while minimizing waste energy. Availability, or exergy, helps engineers determine how much energy can still perform useful work. Through proper design, insulation, reduced friction, and waste heat recovery, thermodynamic system becomes more efficient and environmentally friendly. Understanding these concepts is important because efficiency improvement plays a major role in modern technology, industry, transportation, and energy conservation. In conclusion, this module helps us understand the concept of exergy or available energy, which shows how much useful work can be obtained from a system. We also learned that irreversibilities and energy losses reduce the efficiency of machines and processes because some of the energy is always wasted, usually as heat. Through studying efficiency improvement, we discovered ways that minimize these losses and make systems perform better. Overall, this module highlights the importance of using energy wisely and efficiently in engineering and everyday application.